go. Thanks for the reminder. Otherwise, I would have forgotten. Don't want to do this. Okay, so back to the class. We are now moving on to topic 6. And before we go on, let me just double check that I am recording the right channel. Yep, it is. Okay, that's good. Okay, so now we're moving on to top-down design, which is it's not really as intensive as pre and post conditions. There's not a whole lot of math in this particular module. It just kind of talks about the general approach of top-down design. Why do we need it and what it is? The usual way I start with this is to use maps.google.com as an example, so that people understand the general concept of top-down design. Where's ARC on this map? Well, I know it covers the area of ARC. I'm asking, where's the text that says American River College?
It's not on
It's
there.
not on it. Why not?
Because the scale is too small.
The scale is too small and the resolution of the projector is limited. Let's just say that we can have a projector with unlimited resolution. If it needs to be, we can have tiny text on the screen this big. Okay? Or we can have a super huge big screen TV, so that we can display text like American River College when it's zoomed out all the way to see the continental 48 states. Okay? Would that be a good idea?
No.
Okay? How many people remember back in those days before GPS and smartphones, when you need to go to a new place? Let's say, I have to go on a trip to Los Angeles, and I have to go visit, somebody which I have never visited before. Without GPS, without having to ask for directions, what do I have to do back in those days? I have to get paper maps. Exactly.
Yeah.
So first of all, I will go to my dad or my mom, who is a member of AAA. Walk into the AAA branch, get a huge pile of maps. Yep. And okay, let's just say that I somehow successfully navigated to Los Angeles, which is not too hard because the highway has signs. 400 miles to Los Angeles, right? So that's pretty easy, as long as I stay awake on Highway 5. So let's say I get to Los Angeles. Okay, now I have to find a street address. Okay, and I know it's on the map. Okay, the map has all the details. What happens if I don't have the index on the back of that map?
You have to search everything.
You can't
find the street name.
You can't
Yep.
find the little code.
And do you think that's an easy task? Can I do it in like 5 seconds? Oh, okay, it's right here.
No.
If you're really lucky.
Only if I'm really lucky. But why? How many street names are there on that map? Just a typical,
Los
map.
Angeles?
Well, they probably break Los Angeles into multiple parts
I'm
anyway.
sure they do. City
So I'm just saying, on one single map, how many street names do you think are there on one single map?
Several hundred.
Easily several hundreds, okay? Several hundreds. And for me to scan through a few hundreds of names will take time. It's not something that people can do easily unless you are Rain Man. Rain Man can probably handle that with no problem. But since most of us are not Rain Man, we cannot do it very quickly. And that's why when you display a map, like Google Maps, it does not even try to display, it does not try to display too much stuff. This is already too much stuff, okay? Just imagine if you do not know the geography of the United States, and I ask you, where is Philadelphia, okay? If you don't know the general geography of the United States, you have to scan, for Philadelphia. Now we can do it pretty quickly because we know it's in Pennsylvania, and Pennsylvania is in the East Coast. So even if you're not that familiar with the United States geography, just knowing it is on the East Coast, that means that you only have to scan this much. Oh, here's Philadelphia. But if you don't know anything about the geography of the United States, even this is exceedingly difficult to find items. Is that making any sense? So that means for someone who does not understand, who does not know the United States geography, this is already too much. Maybe we should only display the name of states. But then how do I know how to go from Sacramento to Los Angeles? What highway I should be taking, and so on and so forth. I cannot from this level of the map, okay? Because it's only displaying the big items. It does not display the details. It cannot display the details because if it did, I cannot search for items. Okay, it would be too many things to search at the same time. Is that making any sense? Why we have a dilemma here? Okay, on one hand, I want to display more because I want to know the details of how to go from Sacramento to Los Angeles. But on the other hand, I don't want to display that much information because if I can display all the highway interchange and all the highways from Sacramento to Los Angeles, this entire map will be overlaid with highways, interchanges, and whatnot. So it will just be very, very busy. And if I don't know that California is over here, I will have to search through all that little details in order just to find California. So that's why we can zoom in. Okay, we don't display too much stuff on one single screen, but if we need to know more, we can zoom in. So now I zoom into Sacramento, and we have Los Angeles here. And at this point, I can kind of tell that Highway 5 is probably the best route to go from Sacramento to Los Angeles. Okay, because I just zoomed in to display more details. And if I zoom in a little bit more, I can see all the smaller towns along the way. And there are no Costco's until like way down there. I know that part. I think Burbank is the first place that has a Costco after Stockton.
Really?
Something
Now,
like that,
I don't.
Tracy
What about
has a
basic-
Costco too, but there's nothing in between because no one on Highway 5 ever stops to go to Costco.
Oh, that's true. Maybe on 99.
99 is better,
Yeah.
much better in terms of
Better.
Walmarts and Costco.
Yeah.
But when you're on Highway 5, there's nothing until you get to Burbank. Okay, so now I can see that Los Angeles is here, but I cannot find the streets that I want to go to because if I display all the streets at this level, it'll be way too much stuff for me to search through. It's not because of the resolution of the screen, it's just that if I try to display too much stuff at the same time, it becomes difficult to find something. Okay? And that's the whole idea. If you zoom in some more, then you display more
Wow.
details. If you zoom in some more, you get to see more details, and so on. Okay? Most of you have already used Google Maps and you know what it is. But it's the same thing with programming. Okay? It's the same thing when you have to write a paper in an English writing class. If your English writing class is asking you to write a 10-page analytical paper on some particular topic, do you just sit down and start with the first sentence and 2 hours later you're done with the whole thing?
No.
You just work on it sequentially. No, well, you can do it with maybe a 3-paragraph, short, submission. But when you're talking about a 10-page, paper, most people cannot do it that way. Why not?
Well, there's a
Too much
process.
to do at a time.
Too much to do, too much for your brain to track
Right.
at the same time. Okay, so what do you do instead when you have to write a 10-page paper?
Break it down first.
You have to work with the outline. The outline typically only has 4 or 5 items, and then you look at one item in the outline and then say, okay, how do I expand this? What do I need to include in this section? Right? You just kind of work on the section by section, and then for each section you apply the same technique. You break it down into like 4 or 5 parts, and then for each part you think about, okay, what do I need to specify in that part? Pretty much the same way as we navigate in a map. Are we kind of convinced about all these things that we normally do outside of the context of programming? Okay. So when we talk about programming, there are other considerations on top of what we have already talked about. So let me pop up the screen here. Well, the bottom line is we cannot handle too much details all at once. How many individual items can we handle at any particular moment in terms of our short-term memory?
Was it about like 3 or 7?
Seven, I think.
It varies from one person to the next, but I think it will be rare if someone can handle more than 20 at a time. Okay, most people believe it's somewhere between 7 to 8. Okay, It depends on whether you just have coffee or not. So there are many other external factors that can change it. But no more than 20 most of the time. But in programming, there are additional restrictions. How many lines can you fit on one page when you display your code on screen? That's one of the restrictions. Okay? So how many do you think you can fit on the screen? And still be legible?
15?
40-ish.
I would say
Probably
if you
10.
How
really...
big is your monitor?
Well, let's say you go for a regular size monitor you can buy from Costco. So let's go do some calculations. Okay. So a modern monitor these days has about 1080 pixels vertically, at least. Okay. The smallest font that I can read will have 8 pixels vertically. That's 135 lines vertically. But since my editor is not the only thing I want to display on my screen, because when I write programs, I would typically have to, refer to other documents. So typically, this number has to be, halved, so that I have additional screens to do other things. So as a reasonable estimate, 60 or 70 lines will be pretty much the maximum for myself. Okay. So let me ask you another question then. What if I have one single algorithm that is 500 lines long? Well, first of all, it won't fit on one page, for sure.
Screwed.
For sure.
Yep. So the next question is, if I have an overall construct that spans over pretty much the entire 500 lines, at the end of the loop, let's say it's a loop, how do I find the beginning of that loop? I can try to use the margin. I can try to use the indentation as a clue of where is the beginning of that construct. But it will still be a big hassle to page up and keep my eye on that column and say, okay, when do I see the beginning of this loop? When do I see the beginning of this loop? Okay. Now, unfortunately, this is not uncommon when people write programs. Okay. When people write programs, maybe it started off as a 20-line subroutine or a 20-line algorithm, but as they add more and more and more logic, they just keep adding stuff into the algorithm, and in the end, they end up with a 500-line algorithm. In the good old days, when we still use paper a lot, this is what people do. Okay, we have 500 lines. Each page can fit about 66 lines using 12-point font. And this will span over 8 pages of text. But in the good old days, we have a slight advantage because we have fan-folded paper. Okay, with fan-folded paper is one continuous piece of paper. So now you have approximately 8 feet of paper of your printout of your one single algorithm. You lay it out on a big table, a long table, or you can put it on the floor. And then you take a long ruler and try to match up the indentation of the constructs. Okay, not good. Okay, I can tell you that it is not good. Okay, so that's another reason why I want to restrict my algorithms to fit somewhere between 20 to 40 lines, so that I can comfortably display one single algorithm on the screen all at once. So at least I can see the beginning and the end of everything on one single screen. I don't have to page up and page down. Is that making any sense? That I want to fit everything on one page? Yep.
So can you split an algorithm?
Yep. That's the whole idea of the top-down design approach is you try to not specify the details of doing something and just say, oh, we have to do this one thing here. I don't quite want to tell you how to do it. We just know that it has to be done. Yep.
Is this the formation of classes?
Separate classes, you're talking about object-oriented programming.
Yeah.
Classes is one way to organize your code, yes. But in this class, we are not even quite there yet. We're just talking about subroutines. Okay, subroutine is the first level of organization. And then the object-oriented programming, takes it one step further and use data type as another way to help organize stuff. So in this class, I don't think we'll get to object-oriented programming. We'll see whether we have time at the end of the semester. Okay. So in terms of programming, we have special considerations, because we want to fit the entire algorithm on one single page. But you cannot just use 40 lines or 80 lines to express every algorithm, because there are complicated algorithms that won't fit in 40 or 80 lines. So the way we do it is to be lazy. We just say on one line and say this is what this line is supposed to do, without spelling out exactly how to do it. So I'll use an example to illustrate it. And this is also an example to illustrate how I would write an algorithm. In other words, how to design an algorithm. Yep.
So can you like reference like other files or whatever? So like you could say this is what I want, and then you go over here to look at it and do
Yep.
it or whatever.
Yep. I know I should not be doing this, but let me just point you to what would be helpful in your case. Okay, because what you're talking about are subroutines. It's a topic that we will talk about later, but at this point we just want to focus on the concept of breaking a big problem into big pieces first.
Okay.
And then we look at each piece and go like, okay, is this piece still too big? Okay, if it is, break it up into smaller parts. Okay. But the other purpose of this module is to illustrate how I would design an algorithm to solve a particular problem. So it's kind of like a multi-purpose module, because it helps to illustrate more than one single concept. This is the objective of this program. I want this program to find all prime factors of a number. So how many of us still remember how to factor a particular number? Since I teach this class every semester, I have to remember that. Besides, my fifth grader, sometimes will still ask me, how do I simplify this, fraction? Oh, well, you find all the prime factors. Okay, so we'll start with something that's easy. Okay, something that is obvious. Let's start with, say, 35. 35 is really easy. 35 is 5 times 7. Okay? Okay, because I find the 5 is a factor of 35. Let's just say that I don't know at that time that 7 is a prime number. So the next line is going to go by, okay, can I factor 7? No. Well, the answer is yes. 7 is its own prime factor. But then what is remaining is only 1, and 1 cannot be factored, because 1 is not even a prime number. Okay? So that's an easy case. Let's try something a little bit more complicated. Okay. So this is the number that I want to factor. The reason why I don't want to just use a simple example is because if you use a simple example like this, and I ask you what is the structured approach to factor a number, you cannot tell me. If I ask myself the same question, given only a simple example like this, I could not ever answer that question either, because I can just eyeball it. Okay? We know 35 is 5 times 7 just because we can memorize the multiplication table. In other words, we don't have to invoke any structured thinking to get this done. Now, with a number like this, I cannot just say, oh, it's 2 times blah, 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 blah. I cannot spell out every prime factor just by looking at the number. It forces me to use a structured approach, a mechanical and structured approach to solve the problem. And that's why we like big numbers, not small numbers. Okay, so this is going to be, what,
28067.
067 times 2. So I'll put the prime factor first, and then the second half is 28067, and can we factor that number? First we check for 2. We know that there are no 2s, no 5s for sure. How about 3s? 10, 16, 23. It is not divisible by 3. We don't have to try 5. We try 7. Okay, it's 4. Nope, it's not divisible by 7. We try 13, and so on. Okay? We check all the prime numbers.
What if it is a prime number?
Well, let me show you guys how. Okay, this is a little bit ahead of what we have to talk about, but my objective is just to find one prime factor of this number. Because my interest is not really just finding a prime factor. I want to find all prime factors of the original number. But it doesn't hurt to illustrate the technique. At this point, we'll come back and talk about this technique later on. I use OpenOffice, and we don't need to recover that. Okay, so the technique is to do it like this. So I have to look at a number. I look at all the potential factors. Okay, we start with 2. I know 2 is not smart because we know this number cannot have a prime factor of 2. But that's okay, it's not wrong. Okay, 28067. And then we say, what is this number? Okay. Modulus 28067. We'll talk about all this stuff later on, so don't worry if you don't know what I'm talking about here. This is the remainder. Okay, column B is the remainder of the big number that we have divided by the one in column A. So what I can do is I can just replicate this. So 13 is a prime factor already. Okay? Yes, I kind of cheated. But this, I will come back to this slide here later on. It has, another value in our discussion here. So here we have, 13, and of course I can always just kind of spell out the exact number, quotient. So we have 28067 divided by this number here. And when we get to 13, the number is 2159. 2159. Is it? I didn't know. You can remember? It is?
It just looks like one.
Okay, let me test it. 2159. So I'm just going to cheat a little bit here and change these numbers to 2159. And then we can just take all these. Okay, so far we haven't found, we found one, 17. No, that cannot be right.
Yeah.
It is?
13 and 17 are both factors of the 28067 number.
Well, then how come I stopped it?
Oh, I haven't updated this one yet.
Yeah.
So I have to update this one to be 2159. Okay. And 127. Okay. But I still have to do it step by step. Okay. After finding 2 and 13 are prime factors, I have 2159 left. And according to my trusty spreadsheet, 17 is the next one, times 127. And then we have... Sorry?
I think it was line 16.
Line...
On the, I think it was 16. Oh, I'm
It's
sorry.
7.
I was looking at row 7.
Yeah, this is row 16. The factor is 17. Okay, and then we have 127 left. And with 127, I'll just... I think 127 is a prime number, but I'm not 100% sure. So we'll just go ahead and let the spreadsheet figure it out. And, yeah, it is. I only have to do it up to this part here. Okay, in other words, by the time I have this table, I know 127 is a prime number. I don't even have to go all the way to 127. I'll explain why later on. But 127 is a prime number itself, so it is itself times 1, and I can stop. Is that okay so far? So it is a gradual process. For every step, I find one single prime factor. I have whatever is left, which is the quotient of the original number divided by the prime factor, and then I do the same thing to the other number. And I keep doing this until what?
So we can reach a prime number.
Until I get to 1.
1.
Until I reduce the whole thing to 1, then I know I'm all done. Is that okay? So when I get to the point where the number I have to factor is 1 itself, then I can stop, because I know at that point it doesn't make any sense to try to factor anymore. Is that okay? The gradual process of finding factors? Okay. So if that's okay, then we'll go ahead and try to write an algorithm to do it. So this is the first time that we try to design an algorithm to solve a particular problem. So this is basically a demonstration of how I would start with writing a program, the algorithm design itself. I will start with revision 1. Okay, in other words, I will only work on this step by step instead of saying, oh, I know this entire algorithm, this is it. In revision 1, the only one thing or two things I want to identify is what kind of control structure do I need? In other words, can I do this with one single sequence of assignment statements? Probably not. Can I do it with one single conditional statement? I come in here, I branch, I do something over this side, or sometimes I go over this side to do something, I merge, and I'm all done. Probably not. Because is this a repetitive process? Am I doing something over and over again? Okay. So that means I need some kind of a loop. But at this point, I cannot pinpoint, am I going to need a pre-checking loop or am I going to need a post-checking loop? Well, since I cannot tell, I'll just use a undetermined type of loop that I'll just say loop and loop to say that we have to do something again and again, but we don't know whether we have to do a pre-checking or a post-checking. But regardless of whether it's pre or post-checking, do we think that we have to exit from this loop? Yeah, because by the time we get to 1, we want to get out of the loop. So we do get out of the loop at some point. So then we say exit when something. Can you describe in English when can we stop doing this repetitive process?
When you read your prime number.
When I get to a prime number or the number to factor is 1. Okay, so that's one way to describe it. So I'll just say
when the only factor is 1.
Factors are the number itself and 1.
Yeah.
I'll just do it like this. Okay, exit when the number to factor is 1. Okay, so even when it's a prime number, I don't know it is a prime number until I try to find a factor of that number. And that's why I can only stop when the number to factor is 1 itself. Okay? And I call this revision 1 of my algorithm. Oh, so that means we have to go through a lot of iterations to get to the actual algorithm. And that's very typical when you have to write an algorithm to solve a problem, is you cannot just start with line 1 and expect you to be able to just write sequentially how to work out the algorithm. You have to work step by step, and each step you add a little bit more to the algorithm itself. Okay. So in revision 2, I think what I can do is to improve this a little bit, because this is a little bit vague. Okay, the number to factor is 1. So in revision 2, I'll just use variable names to make it more precise. So I will say the number, let's call the number to factor n. Okay, in other words, from now on, I refer to the variable n as the number that I'm factoring. Well, immediately I can use it, right? Because I can just say when n equals 1. Okay, I'll call this another revision. So each time I'm only doing a tiny little bit of refinement, not a whole lot. Great. Now this is already making a lot of progress. Because if you think about it, 1, I have identified this is a loop. I have to use either a while and while or a repeat until. That's good. That is useful information. But even more useful is I have identified when I can get out of the loop, when n equals to 1. Let's say n does not equal to 1 to begin with. Okay? Because if n always equals to 1, as a problem to solve, this is not a problem because n being 1 cannot be factored. So that means most of the time, if not all of the time, somebody will give me a number that is greater than 1 and ask tech, can you find all factors of this number? So that means n usually is not 1 to begin with, but I can only leave when n becomes 1. What do you think has to happen in the loop? something has to change n in the loop. Does it make sense?
Yes.
Does it make sense that when n is a part of the exit condition or the only variable in the exit condition, there has to be something, some logic in the loop itself, so that per iteration I will be making changes to n. Okay, so we'll go ahead and have our third revision. The third revision is to do something like this. Okay, let's go back to the example that we did by hand. This is one iteration. What did we do in this iteration? We found that 2 is a factor of the original number, which is 56134, right? This is my next iteration. What did we do? We found that 13 is a factor of 28067. This is my third iteration. We found that 17 is a factor of 2159. Okay? So what exactly did we do per iteration? Just describing in English, no need to use in the pseudocode notation at this point.
Found the lowest prime number that was a factor of the
Okay.
original number.
Find a prime factor of n, right? And then what else did we do per iteration? How do I get to this number that I used in the next line?
Divide.
The number by that.
Okay, so probably it would be a good idea to print the prime factor, because after all, the program is supposed to print all the prime factors out, otherwise it's not going to be very useful. And then the last thing to do is to divide n by the prime factor. Okay, it's kind of vague,
Still
it's all
finding
written in
y.
English. Yeah, we're still searching for y,
Still
right?
searching for y.
We're still searching for y.
Hit Control K.
Control K.
It should take it off.
Nope.
No, it's up in the search thing. Clear highlight. Control Shift K. That's what it is.
Or I can just do this. No.
Right that second
Control
line.
Shift.
Shift Control.
Shift Control K. Go. Okay, so in revision 4, I will try to use more concise and more precise notations. So I'll copy this code here, and I'll say, okay, what can we do to make it more concise? Finding a prime factor f of n, I don't think we can simplify that much. Printing the prime factor, divide n by the prime factor. We can do something about this step here. N gets n divided by the prime factor. Is that okay? But we are still referring to the prime factor as quote unquote the prime factor, okay, which is a lot of typing and it is still kind of ambiguous. So what about we just introduce another variable? Okay, we say let f be the prime factor. Well, that makes it a little bit easier. Find the prime factor of n, call it f. We want to print the prime factor, which means we're just printing variable f. We want n to become n divided by the prime factor, which means n becomes n divided by f. Are we doing okay so far with this? Okay. I have just used top-down design. Why do you think I have just applied the principles of top-down design? Did I spell out how to find a prime factor of n? Nope, I'm just saying that let's say we have a way to do it. Okay, stick it here. In other words, when you look at all these lines, this line here does not spell out how to do it. It just states what needs to be done. That's top-down design. Okay, because I don't want to specify all the details. Maybe I'm just lazy. But regardless, I'm not saying how to do it because I don't want to focus on that part just yet. Are we doing okay so far? Okay. So in revision 5, we can probably go ahead and determine whether we need a pre-checking loop or a post-checking loop. What do you think? Do we want to check the condition before one iteration, or do we want to check the condition after one iteration, at least one iteration?
Before factor. after? Just post-checking?
It depends on the assumptions.
We
Okay,
wanna see
so
what
both can work, but it depends on the assumptions. In other words, do you think someone can give me and say, hey, tech, n equals 1, go ahead and find me all the prime factors of 1. If someone can give me an input like this, I need a pre-checking loop because I need to make sure that I don't go through at least one iteration. On the other hand, if the person says, oh, tech, you know what, you're guaranteed that n is greater than or equal to 2, then I can use a post-checking loop. Now, which one is safer?
Pre.
The pre-checking loop is safer. So we'll just go ahead and use a pre-checking loop here. In other words, from revision 4 to revision 5, all I'm doing is to say, let's get rid of the loop and loop here and substitute it with an actual loop structure. In this case, it is a while, blah, 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 do, and while. And the content of the loop is exactly the same. I left the condition blank because I want you guys to tell me what it is supposed to be.
N is greater than 1.
Okay? And n is greater than 1 or just not equal to 1.
Okay.
Either works. This works too. So this is my general algorithm to find all prime factors of a number. Are there any questions about the algorithm to find all prime factors of a number? Okay? Assuming that we have a reliable way to find a prime factor, of n and call it f, assuming this step here, is something that we can do, this algorithm is good to go. Yep.
So, if you made it while n is not equal to 1, then people could give you negative integers.
Well, that depends on whether you can make that assumption or not.
Okay.
Yeah. But technically speaking, we stop when n equals to 1, and therefore, based on the assumption that we have made that n has to be at least 1 or at least 2, then greater than it's going to work.
Okay.
Okay. Well, this is good. Okay, we have just finished an algorithm, step by step. Unfortunately, later on, I found out that nobody has written the algorithm to find a single prime factor given a number. So now it is up to me to also specify that algorithm. But this is top-down design already. This is the map of, this is the map that goes from Sacramento to Los Angeles. This is Los Angeles. Okay? When I get to Los Angeles, I still need to know how to get to the street address, right? So I need to zoom in now and look at this particular line and say, but how do we get that done? Okay, so this becomes my new problem. And I will go here and say, but how do we find a prime factor of n? Basically, that's my new problem. Well, so this is where having the example that we had earlier, the spreadsheet, is going to be helpful. Okay? This spreadsheet is going to be very helpful because it shows us the process of doing things. Now, this one is not really that useful because it. Let me go back and undo a few steps here. This would be a good one. Yep. This would be a good one because we're trying to find a prime factor of 2159. Okay? And what number did I use first to check it?
2.
I used 2. Would you?
Yes.
Probably not, right? As a person, you would not. Okay? Because as a person, let me just spell out the number that we have here, 2159. So this is 2159 is the number that we want to find a factor of. You would not try to, as a person, because you have rules of thumb, which is, if the least significant digit is not 0, 2, 4, 6, or 8, then you know for sure the number cannot be divisible by 2. Okay? You also have one rule of thumb for 3. If you add up all the digits, in this case 2 plus 1 plus 5 plus 9, if that number, the summation, the sum is not divisible by 3, then you know the number itself is not divisible by 3. That's another rule of thumb. If you look at the least significant digit, in this case it is 9, if it is not 0 or 5, you know it is not divisible by 5. So you have all these rules of thumb that you can apply normally. So the question is, should I try to encode all that rule, all those rules of thumb? That's the question.
No.
The answer is no, but why not?
Because the computer does it so fast, it doesn't matter if the computer has to go through 2, 3, 5. Who cares? It's milliseconds or whatever. But for you to write it all, that it would have to do that
Exactly.
thinking, it would take a long time.
And there's one other thing, but what you said is absolutely right, but there's one more thing. All those tricks only work with what representation? Base 10. Okay? All the tricks that I just talked about, they only work when you're dealing with base 10 numbers. If you're working with, say, base 2 numbers, some of those tricks don't work anymore. So that means in order to apply all the heuristics, all the rules of thumb that we have as people, you first have to convert the number from binary, which is the internal native representation of numbers. You have to first convert that into base 10, and then you can use all those rules and see if you can find how many factors. We only have rules for 2, 3, and 5. Going through all that work just to check for 3 possible prime factors is not worth it. It is possible, it's just not worth the time to do it. Okay, so that explains why I'm starting with 2, even though a person would not have started with 2. Okay, going from 2 to 3, same reason. I don't want to apply my rule of thumb for 3 because it's too much trouble to go through. It's just so much faster just to divide it by 3 and find out what is the remainder. The remainder is 2. Okay, that's easy. And I think I forgot to update the other column. Okay, there we go.
Yeah, because 17 is 127, so that's right.
Okay, it is? Okay.
Yeah.
Okay, it's still 0 here. That's good. Okay. But this seems, awfully dumb to me.
Yeah.
Trying 4 as a possible factor. But okay, now we have to think about it may be dumb, but is it wrong?
No.
It is not wrong, because what would make it wrong? Wrong means if I try 4 as a potential factor, and if it is possible for a number to be divisible, if it is possible for 2159 to be wholly divisible by 4, then it is wrong to try 4. But it cannot. Because we know that if 2159 divided by 2 has a remainder, then it has to have a remainder when it is divided by 4. So that means this step is only redundant. It does not have to occur, but it will never give me the wrong result. Is that clear? I mean, does everybody understand why I said this step is not very smart, but at the same time it is not wrong either? How much logic do you think I have to go through to skip 4? 4 is not a big deal. Okay, you can probably write some special cases and say anything after 3, you can just skip, every other number, right? So after 3, you just go for 5, 7, and then 9. But wait, Tack, it's not very smart to check with 9 either. Well, then you're adding additional logic to skip all these obvious composite numbers, and guess what? You're complicating the program again. And yet it is not wrong to try 9 because it will never give me the wrong result. It is just wasting time to perform one step that otherwise does not need to happen. In other words, if you try to say that 10 is also something we should not check, 12 is something that we don't need to check, 14, 15, 16 are things that we don't need to check, you're adding all these special rules, and that makes the algorithm a whole lot more complicated. Yep.
See, but isn't there a level? If you said after 3, skip every other one, you're going to cut the number of numbers in half, and so you could possibly cut your time in half there.
Yes.
But if you went down to 3s, then it's not going to make as big a difference. So
that
it might
true.
be prudent to do the first level and not subsequent levels. Does that make sense?
Mm-hmm. Well, the price you pay is low, but the benefit seems to be enough to justify the cost. But as in a class like this, I don't even want to think about it. Okay, in a class like this, I want the simplest possible algorithm even if it is not efficient at all.
Facets, okay.
And in that case, you'll be halving, the amount of time. But I will show you another trick later on that is not just halving; it is taking the square root of the time.
Okay.
Now that is worth doing.
Gotcha.
Okay, so that's why I will keep doing it like this, because it's just a whole lot easier to specify the logic to try 2 first, and then 3, and then 4, and then 5, until what? Until the remainder of the division is 0. Right? Okay, so let's go ahead and see if we can specify that logic in an algorithm. So once again, this is an illustration of how do we design an algorithm to solve a specific problem. So we start with revision 1 again. Do you think this is a repetitive process? Looking at this slide here, and I'll just erase the part that is not needed. Do you think this is repetitive?
Yes.
Yeah.
Okay, very good. If it is repetitive, we say loop and loop, not knowing whether it's a pre-checking or post-checking loop beforehand. We'll just say it is some kind of a loop. Do we want to exit from this loop at some point?
Yes.
Okay, so we say exit when,
Remainder is 0.
and when the remainder is 0. But the first time we'll just say when f is a factor of n. Okay, in other words, I don't even go that one step further to try to express it using conditions and comparisons. I just want to use the English description of when do we need to get out. In other words, in the spreadsheet here, I can basically just add one more row, insert rows, and say this is my potential factor f, this is my n. Right? This is the remainder. Okay, this is the remainder, and this is my quotient, or this is the result of the division. Okay. So in the next step, in revision 2, I'll just make one slight modification, which is, there has to be a better way to spell out to say f is a factor of n, and this is when it makes sense to use expressions and comparisons. And it is n divided by n mod f equals to 0. The mod operator is kind of like a division operator, except it does not return the quotient of the division, it returns the remainder of the division. Let's go through a few examples. What is 6 mod 2?
0.
Okay, what is 15 mod 4?
3.
Because if you divide 15 by 4, the quotient is 3, but with a remainder of 3. Okay. What about 1 mod 16?
0.
It's 1. 1 divided by 16 has a quotient of 0, but a remainder of 1.
Okay.
Okay? So the mod operator is nothing more than, kind of like a division, except we don't care about the quotient, we only want the remainder of the division. So that means, this term here is referring to the remainder of n divided by f. If n divided by f has a remainder of 0, then we know f is a factor of n. Okay? So we'll call this another revision. Yeah, we made some progress. Okay, great. This is making really good progress because this really spells out what the algorithm has to change in order to get out of the loop. Because these are the two quote-unquote variables, but which one is a true variable from the perspective of this algorithm? In other words, if someone says, Tech, can you go find, a prime factor of 2159? And I say, I know 2 is a factor of 2. Would that be a good answer? No, because I'm not answering the question. So I cannot change n. I cannot change the question itself and say, I know 2 is a factor of 2. I have to answer the question by figuring out what is f. What value of f will make this entire thing 0? So that means in the loop itself, which variable should be changed? I cannot change n, but I can change
F.
I can change f. Okay, but how am I changing f for each iteration? You look at this spreadsheet here. This is f in the first iteration, second iteration, third
Changing it by
iteration.
one.
I'm just adding 1 to it,
Yeah.
right? So that means I can go back here and I can say in the next revision, in revision 3, I just have to say that for each iteration, f gets f plus 1. Now this is very easy to express, but if I want those also special rules to say if it is greater than 3, skip 1 every time, that makes it kind of more complicated. It is not wrong to do it. It's just we don't want to handle the extra complexity of the optimization. We just want something that works. May not be the most efficient way, but we just want it to work. Is that okay so far? There's nothing wrong with being inefficient at this point. We just want it to be correct first. And this also applies when you get to the CISP360 or just about any time you write a program. You don't want to think about efficiency right off the bat. You want to think about correctness first. Okay? Because a lot of times when you try to optimize something, you have to think about all the special cases. Oh, in this case, I can do this trick. In this case, I can do this trick. In this case, I can do this trick. And before long, the algorithm will have so many special cases, it makes what's difficult. It makes testing it difficult. Because all these different branches, they all have to be tested. So that means you have to feed your program all these special cases to make sure that the entire algorithm works with all the optimization. But in this case, without any optimization, it's not really hard to see that it is correct because I don't have any special cases to consider. We're almost done. The only thing left to do is to say, oh, but what is the first value of f that I should use in this expression here?
2.
We want it to be 2, right? And there are 2 ways to proceed from here. One way to proceed from here, I will call this revision 4a. Okay, 4a is one way to do it. In 4a, I will simply initialize f to 2 first, and I use a pre-checking loop to do it. So basically, the pre-checking loop will say, while n mod f does not equal to 0. Because when n mod f does not equal to 0, f is not a factor of n. In that case, I'll move on to the next one and try again. That's the first way. And there's a second way to do it. Revision 4b is the alternative. In this case, I initialize f to 1. But instead of using a pre-checking loop, I use a post-checking loop. So the first thing I do inside here is to say f gets f plus 1. Then I specify until n mod f equals to 0. Is everybody convinced that these 2 loops are equivalent when it comes to finding a prime factor for n? If they are equivalent, does that mean that you can pick either one? In terms of correctness, yes. But is one preferred for one reason or another?
Yep.
Which one do you think is better?
Pre-checking.
4A.
4a, and what is the reason?
You don't go into a loop unnecessarily.
You don't get into a loop unnecessarily, and that's true, but there's one more thing. The second thing, when you look at efficiency, yes, 4b is slightly less efficient because you have to go through 2 assignment statements before you get to this statement here. But that's not the reason why I do not like it. I do not like it because in order to figure out what is the first value that you will use for the mod operation, you cannot just rely on the initialization out of the loop. You also have to factor in, I have to go through 1 iteration. So there are 2 things that you have to go through in your mind just to figure out what is the first prime factor that I'll be testing. Whereas in revision 4a, it is straightforward. Okay, I initialize f to 2, and guess what? I use it right away and test it. So for that reason, for clarity reason, 4a is a better solution. Even though both will get a job done, if you have a choice, choose 4a. Is that okay so far? Why we prefer the 4a, even though 4b will get the job done as well? Okay. So we have we're done. Okay, we are done with the entire algorithm because I have just spelled out this part here, the highlighted text here, basically can go into this place and the entire algorithm is specified. Okay, the printing operation is typically supported by the language itself, so we don't have to spell out how to print a number because it is not. It's usually very common for most programming languages to have a way to print a number. Okay, now this is all good, except remember what I said a little bit earlier, that we can optimize this algorithm so we can actually use only up to the square root of a number. Okay, let's see whether that makes sense or not. Let's see. Let's go back to the spreadsheet. Nope, that's not the spreadsheet.
On the end.
And this time, I have made some changes already. I need a big prime number. 129. $129 is big enough that we don't know.
It's not divisible by 3. 129.
Yeah.
It's not divisible by 3.
Oh, it is.
Just do 127.
127 is not a prime number. It is a prime
Yes, it
number.
is.
Oh, okay, great. Okay, we can just use 127 then. Okay, this is 127, and turn this into 127. That part is not even useful anymore. And this is 127. And my claim is this is all that I need. Okay? Because using this program, using the pseudocode that we have just derived, it will have to test everything until f becomes 127. Then we have 127 mod 127 has to be 0 because we are dividing the number by itself, so there's no remainder, then we get out of the loop. But my claim is we don't have to go that far. My claim is we only have to go all the way up to 12. If I can confirm that 12 is not a prime factor of 127, I know 127 is a prime number itself. Now, this optimization is worth doing because you are cutting down the number of calculations by a whole lot more than just 1/2, because it's the square root of the original number of loops that we have to go through. The question is, does it make sense? Does it always work? Well, you can try it out. You can modify the algorithm just like what I have suggested, and try different prime numbers. They will all work out. But can you be sure that the next one will also work? Maybe, maybe not. So what we need to do now is to say, let's go ahead and see if this approach makes sense in terms of mathematics. Okay, that's what we want to do next. So we'll just put a big separator here because this is about the optimization, but it's also about proving a concept is going to work or not, instead of just saying, oh, I tried it a few times, it works in all test cases. It's good, it's comforting that you have tried it out and it works in a few test cases, but it doesn't really guarantee that the next test case is going to work out just fine. So the whole premise behind this optimization is something that looks like this. So we can say let a be an integer greater than or equal to 1. So pick any a as an integer that is greater than or equal to 1. Let b be an integer greater than or equal to 1. In other words, you can pick any a and pick any b as long as a and b are both integers, and as long as they're both greater than or equal to 1, that's cool. The rest will follow. Okay, we define p to be the product of a and b. So a times b is p. That's by definition. Don't ask me why. It is by definition. P as a symbol represents the product of a and b. Here is tax claim. Tax claims with money back warranty. That's typo. Spelling mistake. Is it double R?
2 R's and a Y instead of E.
Okay. With money back warranty. Okay, now here comes the big thing. Okay, the big thing is, well, it's actually not too complicated. the thing is, let's see, a is less than or equal to the square root of p, or b is less than or equal to the square root of p. That's my claim. The other way to look at this, okay, alternative way to look at this, is a times a is less than or equal to p, or b times b is less than or equal to p. They're basically the same thing, because we know a and b are both positive, so that makes these two equivalent. If I did not tell you that they're positive, then it's a different kind of issue. Okay. Does it make sense? But let's try out a few numbers, right? 3 and 4. Okay, a is 3, b is 4. Okay, the end result is 12. Well, I know you guys know for sure that 3 is less than or equal to the square root of 12, because 3 squared is 9, and 9 is already less than 12. Does it make sense? So you can basically pick pick any number, any integer a that is greater than or equal to 1, pick any b that is greater than or equal to 1, and you will see that, oh, well, every number that you pick, this works out. Does that mean that the next number, the next pair of numbers will also work out? No. Okay? In other words, that's not a proof that this will always work. It is simply saying that for all the numbers that you have tried, it worked. It's not good enough in a math class, and it is not good enough to put into an algorithm. Why not in an algorithm?
Because you need to know with certainty.
Because you need to know for certain that it will work in all tests, in all cases. Because if you don't, then your program will work for the most part, but it may fail occasionally. Those will be bad problems to have. Okay, so how do we prove that tag is right? But let me just change the question a little bit and ask you another thing instead, and you can try to prove this one. I only have one type of sock in my drawer. And that is absolutely true. Okay? I only have one type of sock in my drawer. The question is, can I guarantee to have one pair if I just pick any two socks out of the drawer?
Yes.
Yes.
It seems to make sense. Prove it. Okay? How do you prove it? It makes so much sense that you don't even want to think about how to prove it, right? But the proof is easy. You assume that I'm wrong. Okay, you assume tag is wrong. Now what is wrong, what does that mean? That means if I pick two socks out of my drawer, it is not a pair. Okay, fine. But how can you make that happen? I pick two socks out of my drawer and it is not a pair. That means I have at least two types of socks in my drawer, which contradicts with my assumption that I only have one type of socks in my drawer. The contradiction is the proof that I cannot be wrong. In other words, if I want to sum up the technique of proving that I'm right, is I cannot be wrong. Okay? Or if I am wrong in the first place, bad things will happen. It's proof by contradiction. Okay? In some math classes, I suppose they will teach you that trick. Okay? And for those of you who want to understand the power of contradiction, the destructive power of contradiction, you want to go home and watch Dogma, the movie. But in mathematics, contradiction is also a very powerful tool. Okay? So if I want to prove that tag is right, then you want to say, let's assume tag is wrong and see what kind of bad things will happen. Okay? What does it mean that I'm wrong? If I'm wrong, this is not true, because that's my claim. Is that right?
Yeah.
Okay, so I'll just go ahead and do that. So if tag was wrong, then is not true for all possible A's and and B's. Now the A's and B's will still have to, fulfill these requirements, because otherwise, it makes no sense. It doesn't matter anymore. So A's and B's will still have to fulfill this requirement, but for some A that is an integer greater than or equal to 1, and for some B that is an integer greater than or equal to 1, for some reason, this is not true anymore. This is how you prove that I'm wrong. Right? Is that okay so far? Now, what does it mean when this is not true? Okay, so what we'll do is we'll just go ahead and say that if this is not true, what does it mean? To say that it is not true that A times A is less than or equal to B, or B times B is less than or equal to P, isn't it the same as saying A times A is greater than P,
Or B times B is greater than
and B times B is greater than P?
Yes.
Okay, is everybody convinced of this? Okay, let me just say that again. It is not the case that A times A is less than or equal to P, or B times B is less than or equal to P. In other words, the entire disjunction is getting negated. To say this, it is really saying the same thing as A times A has to be greater than P, and at the same time, B times B has to be greater than P. Are we convinced of this or not? Okay. Okay, this makes sense, because there's also a law called De Morgan's law. De Morgan's law can give you this transformation. But regardless, well, let's just say that this works out. Well, what is the big deal? It's not a big deal. Yep.
Why would you have and instead of or?
Because when you invert the logic, it just works out that way. Okay. Let me just prove this. Let me prove that this is right, because after all, we are trying to use mathematics to prove everything. So it would be wrong to say, oh, we can just jump from this step to this step. That would just not be right. Okay, so we'll just go ahead and prove that this is right. Okay, we have x, y as two Boolean variables. In other words, x as a Boolean, as a true-false value, can be true, it can be false. But y, also being Boolean, can also be true and false. So when x is true, y can be true. When x is true, y can be false. When x is false, y can be true. And when x is false, y can be false as well. Is everyone convinced that I have just spelled out all possible cases between x and y? When both are Boolean, they can only be true or false. Okay. So the next thing is to figure out, what is not x or y, which resembles the structure of what we have here, right? We have a negation on the outside and a disjunction in the inside. I just replace this entire expression with x. I replace this entire expression with y. Okay? Nonetheless, we can just go ahead and evaluate. What is the answer of not true or true? False. Okay. What about not true or false? False. False. This is the only time it can be true. Are we doing okay so far? I skipped a few steps, because in the second case, true or false is true by the definition of disjunction, but not true is false. In the third case, kind of the same thing is symmetric to the other side, because in this case we have false or true, but since we have at least one side being true, the whole thing is true. But if the disjunction is true, the negation of that is going to be false. It's only the last case where we have false or false in the inside that becomes false, but not false is true. Is that okay? So this part is not, there's no derivation. It's really just working out the operators. Now we have the other part. The other part is not x as one thing, and use a conjunction, and then we have not y on the other side. So we want to evaluate this conjunction. In this case, x is true, not x is false. Y is true, not y is false. What is false and false?
True.
False and false is false. Okay. In this case, we have x being true. What is not true?
False.
Not true is false. Y is false. What is not false? true. We have false and true. What is that? False. Okay, in this case, we have just the opposite. We have x being false, not false is true. And then we have y being true, not true is false. So overall speaking, we have true and false. What is the answer of that? False. And in the last case, we have not false is true, not false is true. So we have true and true is true. What have I just done?
Explain why not x or y is equal to not
Is
x.
equivalent. Okay, I have proven that for all possible x and y's, this expression is exactly the same as that expression. Is that okay so far? I have just proven this is called De Morgan's law. How does that apply to our thing here? Well, I just skipped one step. The one step that I skipped is this. Not a times a is less than or equal to p, and then we close both parentheses, and then we say and not, oh, okay, never mind. I put the open paren at the wrong place. B times B is less than or equal to P. Okay? Are you guys all convinced that this thing here, it is not the case that A times A is less than or equal to P? Is it saying exactly the same thing as A times A is greater than P?
Yes.
Okay, so now we have that statement. So what is so special about this statement? Well, let's think about this. Okay, if A times A is greater than P and B times B is greater than P, what about the product of A times B versus P times P? Doesn't this imply that A times B times B is greater than P times P?
Yes.
Yeah.
It kind of follows, right? I mean, because we know they're all positive numbers, so we don't have to deal with the sign being inverted and whatnot. This chunk is greater than P. This chunk is greater than P. So when I take the product of these two and take the products of these two, the relationships should still hold up, right? Okay. Now, but this also implies, because I know multiplication is commutative, you can change the order of multiplication and get to the same result. So this can be rewritten as A times B times A times B is greater than P times P, right? But by definition, what is A times B?
P.
Let's go back. By definition, P is A times B.
Yes.
Okay, is that so bad? The answer is yes, it is bad, because I just overwritten something that is not supposed to. Okay, so we have A times B here. Let me just kind of group everything first, so it becomes kind of more obvious of what I'm trying to get to. Right? Because I can put the parentheses any way I want, because the order of multiplication does not matter when you have a series of multiplications. But A times B by definition is P. A times B by definition is P. Let me just match up everything so it shows better this way. I think I have a problem with this. P times P is greater than P times P is a contradiction. It is false. So this is the quote-unquote bad thing that happens when you assume that I am wrong. So, okay, let me get this right. So when you assume that I am wrong, bad things happen. What does that imply?
That you're never
I
wrong.
was right.
Oh.
That I was right. Okay? So I have just proven that this is right. Yep.
Do you use this logic with your wife?
Proof by contradiction. But proof by contradiction is one of the most powerful techniques of proving. Okay, because you're not moving forward, you're not just starting with the premise and saying, okay, step by step we can prove the result. You are starting with the assumption of, let's say it is wrong. Let's say the theorem is wrong. Let's say that particular claim is wrong. Let's see what happens. And then if you can get into a contradiction, then you have just proven the claim has to be right to begin with. It's one of the most powerful techniques in proving something in mathematics. Then the other one is called induction, which is something that you won't encounter until CISP 440. Okay. All right. So we have just spent a lot of time to get this part here. Okay, let me just kind of copy this and paste it to the end because I want to see why it relates to the algorithm that we are dealing with. Okay, this is the claim, and we have just proven it. Okay, so I'm just going to erase the part that that is a little bit hard to deal with. It's easier to deal with the square of A versus P than the square root of P. How does that relate to our algorithm at hand? We are trying to find a prime factor given a number, right? So how does this relate to what we are dealing with?
Well, if the integer that we're trying is
A composite.
a composite or whatever, yeah.
Mm-hmm.
So it'll tell it to stop after it reaches the square root.
Exactly. So this means that if n is composite, now when n is composite, that means n equals to some product, and it is a product of two integers. That makes it composite. Then what do we know?
A and B cannot be greater than the square root of P.
Well, then this has to be true. This has to be true. Okay? In other words, if I have tried all the numbers so that the next potential factor, the square of that is greater than P, then we know the number has to be prime. Because if a factor existed, I would have found it already. Is that making any sense? If 127 is a composite, in other words, if 127 was not a prime number, by the time I tried 12 by 12, 12 times, by the time I tried whether 12 is a prime factor or not, I would have found that prime factor. 127, if it has a factor, now when you have a factor, you have the opposite side, because remember, a composite number is A times B. One of those has to be less than or equal to the square root of the number. If I cannot find a prime factor, and I go from the low end to high numbers up to the square root of that number, I can conclude right away that that number does not have a factor. It is its own factor. So that's why we can do something like this. So this helps to make our algorithm more efficient, because now we can stop. We can stop as soon as f times f is greater than or equal to n. Okay, let's go back, take our algorithm from here, revision 4a, and we'll continue to make our algorithm more effective, more efficient. So that means in addition to n mod f has to be non-zero to stay in the loop, I have now an additional condition to stay in the loop. Because I have to say, I only want to stay in the loop if f times f is less than n. Okay? If f times f equals to n, why do I want to get out of the loop? Because f is a factor in that case. If f times f is greater than n, then I can use the theorem that we just talked about and say, okay, by this time I would have found a factor if n is a composite number. Since I could not find any number up to this point, I know n is prime. Is that making any sense? Okay, so just adding this one little condition here makes it possible for me to get out of the loop much earlier when the number n itself is prime. But then I have a second problem, because by the time I get out of this loop here, f may not be a factor of n, and yet f is not n itself by the time I get out of this loop. So I need a second conditional statement after the loop to take care of that case. So I have to say if f times f is greater than n, then f gets n, and if. Why do I have to do this?
Because it needs to pull out the last factor.
Right. F is supposed to be a factor of n. If n is prime, then it is its own factor, which means f has to have the same value as n. So it has to do with what the rest of the algorithm is expecting from f.
Because otherwise it would get an arbitrary value, like n to 120.
Exactly. It will just get the, exactly, it will think that 12 is a factor of 127 in our case, which is not. Okay. Are there any questions at this point? No questions? Do you think this is worthwhile to do? Adding this logic here so that we can make it exit earlier when n is prime? Now, if it is worthwhile to do you think it is also worthwhile or important to go through this proof here to show that the optimization itself is valid? So in that case, do you think it is important for people who write programs to understand mathematics, at least to a certain level? Okay, so it all kind of ties in together, to basically re-emphasize you can write programs without understanding a whole lot of mathematics, but it helps you to become a more effective programmer if you can apply mathematics when you are programming. Okay, it's not. I don't agree with Dijkstra from the perspective of you have to get a math degree before you can become a programmer. But I think every programmer can continue to grow and become more effective if they just continue to learn more about mathematics. Okay. Are there any questions about this part? No questions? Okay. So if there are no questions, we are done with the top-down design module. We have covered all the material that we need for exam 1. Next Friday, we'll have a practice exam. What a practice exam is just like a regular exam. I will use Moodle. I will basically use the same type of questions as I would in the actual exam, except in this case, I will not grade it. And 2, the score does not matter. It does not change your actual score of this class. Yep.
Are we going to be expected to memorize the sub formula and also the forget formula?
That part is up to you, but I can tell you, since we'll be taking the test in the lab, in the computer lab, it will be open book, open notes, and open web.
Okay.
So I think it is more effective if you can remember some of that stuff, but you don't have to memorize everything because all the class notes up to this point, all the YouTube clips up to this point, the entire internet is at your fingertips during the exam. The only thing you cannot do during the exam is live communication with another person during the test. But as long as you have everything pre-written, either online, on your thumb drive, or something that you can search during the test, it's still good.
So we can watch YouTube during the test?
Yes, you can. Yes. You can watch Michael Jackson. You can watch Weird Al. During the test, yes. Yep.
So when is the test?
The test is going to be 1 week from next Friday, so 2 weeks from today. So that gives you quite a bit of time to prepare. But I will still prepare for the test as if the test is actually next Friday. So when we go through the practice test, you can basically assess how much of the material you're ready for. So that will give you a fairly accurate picture of how you will do in the actual exam.
So we're going to actually do the practice test as if it was the real test we were taking?
I would do it
With
in the
lab?
class.
Oh, we'll do it in class.
I would do it in the class, and since everything is going to be recorded, that will also show you the procedures of how to take the test. Not just the answer to the practice questions,
Right.
but also what you need to do to upload the file and stuff like that, so that by the time we get to the test, there won't be any surprises.
Okay.
And then after that, you also can basically go through that exercise as many times as you want. If you just want to make sure, okay, let's see if I can upload this spreadsheet file in 5 seconds. You can practice it all day long. Okay. Now, what would be helpful for the exam is to have OpenOffice, Firefox, and all the other tools that you need on a thumb drive. The Computer Lab 152 has all of those tools already installed on those computers. But just to be sure, it does not hurt to have your own thumb drive or a little SD card with the portable applications, just in case you need it. Yep.
Never mind.
I installed the Firefox, but I'm having a hard time moving my bookmarks over onto my portable one. So
To move the bookmarks, I think there's a feature to export it.
There's a couple of apps that can sync bookmarks between.
Firefox itself can sync already if you use the later version of Firefox.
Would that be 4? Or does
Yeah,
3 do
yeah.
the
4
same?
has the ability to do it.
3 does as well.
Or
Import
3
There's an
also.
app
Oh,
called
there we go.
Export.
You can back up and restore. Okay, let me show you how to do it. So you go to bookmarks, you go to organize bookmarks, and then you go to import and backup,
Okay.
and it just say backup. It will save everything as a JSON file, and then on the other side you just import it using the same
Import
interface.
from that JSON file.
Yeah.
Gotcha. Okay.
Yep. I think JSON stands for JavaScript something. Something.
Exactly.
Okay, so that answered that question. But now we still have 10 minutes left at least. So we'll go ahead and look at one of the type of questions that I will ask you. It's about pre and post conditions, except I give you the post condition and you tell me what is the pre condition. Okay? So let's go ahead. Let me just go ahead and give you one example on the whiteboard itself, because it really helps to draw the picture first. Okay, let's see. We have. I'll use the editor anyway. So this is a potential question in exam 1. Okay. We have a program starting with, let's say, line 25. And we'll say if x is less than y, and line 26, x gets x plus 1. And then on line 27, else. And on line 28, we say x gets x minus 1. And then on line 29, we have and if. Okay? Fairly simple conditional statement. If x is less than y, we go one route, we add 1 to x. If x is not less than y, we go the other route, which subtracts 1 from x. Okay? And the post condition is like this. The post condition of line 29 is just saying that x equals to, well, let's try 26. Or, okay, let's try 6, 5, doesn't matter. Okay. And the question is, what can you possibly tell me about the precondition of line 25? Okay? Now, why would I want to do something like that? I mean, in actual programming, why would I want to do something like this? Start with a post condition and try to work my way up to the precondition.
If you get an initial result, you want to figure out what was put in.
Exactly. Okay. In other words, if x being 5 is wrong, right after line 29, but that's the first time you can actually detect if something is wrong with your program, this allows you to at least work a little bit backwards so that you can say something about line 25. Okay. Now in this case, I did not tell you anything about y. So the question is, can you also tell me something about y before line 25? And the answer is, you can tell me something. Okay, it's not very definite, but you can tell me something. So let's go ahead and try to work this out. Okay. The best way to do it is to draw a picture first. Okay, draw a picture of the algorithm. And we have enough time to do it. Okay, here's a general picture of a conditional statement. In this case, the question is whether x is less than y. If the answer is true, we go onto this side, x gets x plus 1. If it is false, we go to the other side, x gets x minus 1. That's the general structure of the conditional statement. I told you, okay, that we start with post 29, which is right at this point. And at this point, we know x equals 5. The question is, what do we know at this point? Can we go backwards and say something about that point? And the answer is, surprisingly, we can. Now, if x equals 5 here, and I don't know which way I came from, I probably have to say, well, maybe I came from this side, maybe I came from the other side. I have to explore both sides. I cannot just say that I must be coming from this side or the other side. So that means at this point here, x equals 5 as well. At this point here, x equals 5 as well. Is that making any sense? Okay. Well, but both of these operations are reversible. In other words, if I know x equals 5 after x gets x plus 1, I know x is what? 4 before. Exactly. So over here, I know x is 4. And using similar reasoning on this side, I also know that x equals 6 before I decrement 1 from x. Is that making any sense? And what else do we know at this point? Well, since I am here, we also know that x is less than y has to be false. Okay, so we have to say x equals 6 and x is greater than or equal to y. I just turn the negation and change the comparison instead. What about the other side?
X is less than y.
X is less than y has to be true. Has to be true. Okay. X is less than y has to be true. So we have a conjunction here. Great. Well, this is really useful because these two paths, if you walk backwards, these two paths will merge before the precondition of the entire conditional statement. So what you know before the entire conditional statement is a disjunction of these two. So you know for sure that x is less than y and x equals 4, or x equals 6 and x is greater than or equal to y. Yep.
Did you say that y is greater than 4 on top, and then
Yes, you can.
y is less than?
Yes.
You can put the numbers in there.
Yes, because in this case we know for sure in this branch x equals to 4, so that means you can
Even
actually just
substitute.
you can just change that to a 4. And on this side, since we know x equals to 6, we can also change this to 6 is greater than or equal to y. Now that is useful because when a program crashes or when a program misbehaves, it may only give you certain clues about the variables, the state of the variables. In this case, maybe for some reason I can only output or capture that x has a value of 5. But using the logic of this program and pushing it backwards, I can actually deduce that one of these two has to be true. Obviously, in this case, they cannot both be true because x cannot be 4 and 6 at the same time, but I know one of these two has to be true. Now, but you can see how I can push this even further back as long as the operations are undoable. So that means, I can possibly push this all the way back a few steps until I hit a breakpoint, until I hit a break wall that I cannot pass. If I get to a break wall that I cannot get past, then I have to set a breakpoint at that point and rerun the program using the same conditions if possible, and then I can look at the variables again. Now this is a technique that unfortunately is not used these days anymore because we have superior debugging tools. Okay, do you understand what I mean by that? With better tools, people don't use techniques as much anymore.
They definitely don't use paper-written techniques.
Exactly. In the good old days, when you write a program, let's say in COBOL, and you submit it to a data processing center using a stack of punch cards, do you think you can just change the program a little bit and rerun your batch?
No.
Not on the same day. Okay, so that means you have the entire day to look at the symptom of the program, look at the program, and try to figure out what's wrong with it. Because you cannot submit a job until tomorrow anyway, and it will cost you money to resubmit a job. So that forces programmers in the past to try to deduce a problem as much as they can on paper without having to rerun the program, set up breakpoints, and do all kinds of stuff that we can do now. But it also makes sense in other types of programming. There are certain types of programming where you cannot reproduce the same condition easily. It's called embedded system programming or real-time programming, where the program is interacting with all kinds of stuff on the outside. So in that case, some of the conditions cannot be reproduced. If a condition cannot be reproduced, then maybe this is the only one time that this symptom will show up, because somehow it just has the right conditions for the problem to show up. And if that is the case, you only have one shot using this, this as a clue to try to figure out why the program is not behaving. And I can tell you already just one thing. You might think that oh, but who's going to write programs that are non-deterministic, where a condition cannot be reproduced easily? Think of your mouse. Think of your keyboard. Okay, the software in your operating system that interprets key presses and also mouse movements and stuff like that, they are already non-deterministic. In other words, there's no way you can reproduce exactly the same condition as what I'm doing here on the screen. Okay, because a big factor of that is not the computer itself; it's me. I just decided I want to move it now. I want to go from this window to this window in this direction at that speed.
Yeah.
That condition cannot be reproduced easily, unless you capture everything. Then you can probably replay it in a certain way. So that means this technique is also useful when you're writing device drivers or anything that is low level from the computer's perspective. Right now, there are tons of stuff that is happening in the background that we don't even see. Network traffic. I don't see any network traffic, but it's going on all the time. The timing of the network traffic is once again unpredictable. It is not deterministic. So if there's any type of bug in the network card driver, it is possible they will only occur very rarely, occasionally. And that means, if it happens and you capture some information about it, you may not be able to reproduce exactly the same condition of, what it needs to happen. That also makes this type of technique useful. Okay, so we'll stop right now. I'll upload the second half of the class as soon as I can, and go ahead and do your homework assignment. Oh, one more thing. This is important, because if I don't tell you guys ahead of time, you'll be confused. I changed the nature of the second homework assignment so that you have to turn in a file instead of using the built-in editor, because I think we are having too much trouble with the built-in editor. So in this case, it is just turning in a file to do it. If you have turned it in already using the built-in editor, that's good. I will still grade that one. Yep. Okay. Okay, so you have to be a little bit more clear, medical reasons.
Specifying the situation or something like that.
It doesn't have to be like in details. You just have to say that you notify the professor, after he has dropped, and but it's for medical reasons, and and you back to the class. Yep. So I'm not sure whether I can add it here because I'll be writing in your part.
Yeah.
So you might want to change that before you turn it to me.
Okay.
Okay. Let me turn off the projector first. What's the projector? Oh, thank you. Okay. Let's check out the grades. Your name is.
Like when you go further, it's not.
Okay,
no,
you.
No, I'm talking about the microphone.
Oh, okay.
So they did the first one.